Hi, we are Group 24 consisting of Shengmu, Junjie, and I, Weng. And today, we will be presenting our project on stable matching and deferred acceptance. Let me start by introducing the general problem of stable matching. This problem is concerned with finding a matching between elements that is stable given an order of preference for each element. For example, we have two sets of elements, small a and small b, and capital A and capital B. This table on the left represents the order of preferences for the set small a and small b, and on the right, the order of preferences for the set capital A and capital B. But what do we actually mean by a matching that is stable? So we say that a matching is unstable when there exist matched pairs small a capital B and small b capital A, such that small a actually prefers capital A to capital B, and capital A actually prefers small a to small b. So given the order of preferences in the previous example, this matching on the top is actually unstable because small a actually prefers capital A to capital B, but is matched to capital B. And capital A also prefers small a to small b, but it is matched to small b. The matching on the bottom here is unique. It's the unique stable matching between the two sets for this particular problem instance. In the context of this module, the stable matching problem can be casted as a classical planning problem, where the state space is the set of all possible matchings, the goal state is the maximal stable matching, and the action is the addition of an edge to a matching. The stable matching problem itself is very general. In this project, we focus on stable matching between elements in two distinct sets. In its most basic form is a stable marriage problem, where both sets are of equal size, as we have observed in an earlier example. The problem can be generalized to the setting of uneven sets, as well as associating a quota to each element in one of the sets, which actually gives rise to the college admissions problem or hospital's residence problem. Closely related to this problem is also what is known as the school choice problem, where the preference ranking of applicants are not actually determined by the school, but according to the local laws and policies. As briefly alluded earlier, a wide variety of real-world problems such as college admissions, assignments of doctors to hospitals, as well as internet content delivery can be modeled as a stable matching problem. Hence, being able to find a stable matching effectively and efficiently is very, very important. As such, we will review a few books proposing algorithms to solve some variants of the marriage problem, hospital residence problem, and school choice problem. Specifically, I'll be reviewing this paper on college admissions and stability of marriage by Gale and Shapley, which actually sets up the general framework for solving stable matching between two sets. Shengmu will then review this paper on new algorithms for Japanese residency matching, which more effectively solves the hospital residence problem with secondary quotas on a partition of the hospitals. Junjie will then review what's the matter with tie-breaking, improving efficiency in school choice, which actually improves the stable matching for students in the school choice problem with indifferences in the priority ranking of mainly the schools. In this paper, Gale and Shapley actually presented the first constructive proof of existence of a stable matching in the marriage problem as well as the college admissions problem. And it is presented in the form as an algorithm well known as the deferred acceptance algorithm or propose and reject algorithm. The deferred acceptance algorithm solves the fundamental marriage problem by iterating through the following steps until everyone is engaged. So initially, all men and women are not engaged to actually anyone. And each iteration has actually two steps. The first step being the proposal step, and the second step being the rejection step. In the proposal step, every unengaged man actually proposes to the woman who he prefers the most among those that he has not proposed to. In the rejection step, for each woman who actually receives any proposals, if she is unengaged, she is then engaged to the man who she actually prefers the most among those that actually propose to her. Else, if she's engaged but prefers this particular man over her current fiance, she then cancels her existing engagement with her fiance and gets engaged with this particular man. This algorithm terminates as all men at most proposes to each woman once. Upon termination, all engaged couples will get married or matched, and these marriages will always be stable. Deferred acceptance can be easily generalized to solve college admissions or school choice. We first consider the simpler case of having less men than women in the marriage problem. A stable matching can be found by running the algorithm until all men are engaged to give a maximum stable matching. When there are more men than women instead, we terminate when all men are either engaged or rejected by all women. In the college admissions, where there is actually a quota imposed on each element of the rejecting set, deferred acceptance can be simply modified by considering the top K preferences during the rejection step, where K is the quota, in order to yield a maximum stable matching. We evaluate the deferred acceptance algorithm from the perspective of its computational complexity as well as its intrinsic properties. In particular, as we have mentioned that every man at most proposes to every woman once, it's clear that the time complexity of DA is polynomial, or more precisely in the order of m by n, where m and n correspond to the number of elements in the two sets being matched. In general, the solution of a stable matching problem is non-unique. Having said that, DA returns the stable matching optimal to the proposing set. This is apparent from the fact that engagements stem from the proposals of the men, which are done in decreasing order of preference. As a consequence, the DA solution is also pessimal or least optimal to the rejecting set. Apart from that, DA is also a truthful or strategy-proof mechanism for the proposing set, which entails that the algorithm does not yield a better matching for a man that misrepresents his preferences. On the contrary, it is generally not truthful for the rejecting set. Now, I'll pass on the time to Shengmu to elaborate more on the second work we have surveyed.
So next, we'll be discussing the Japanese residence matching problem. So for the background of this problem, we are trying to match between doctors and hospitals in disjoint regions under regional quota. So what that means is there are a bunch of hospitals in each region. And then in this region, we have a total limitation of how many doctors there can be among all the hospitals in this region. And for each hospital, we also have a small quota that you cannot exceed this number of doctors in my hospital and in whichever hospital in this region. So the current DA solution basically imposes a very strict and smaller than the true capacity of the hospitals, so that to satisfy the regional quota. That means is the current DA solution just try to impose a very strict limit to each hospital in the region, so that the sum of all the quotas among all the hospitals in this region does not exceed the regional quota. But this limit is actually smaller than the true capacity of the hospitals. So in this case, there is a waste, or what the authors call a redundancy problem in the current solution. So the authors propose a new way to do this, and so that to get around that restriction. So okay, a little bit context first. What they call this a contract basically is a potential match between the hospital and the doctor. And then they also create this thing called dummy hospital. What that means basically is to model the extra capacity of the hospital into a separate hospital. So originally we have the hospitals with real capacity X. So this is the true capacity of the hospital. And then first it's divided, basically this hospital is divided into two. One one is a hospital with the capacity limit Y imposed by the original original solution. And then the redundancy or the extra capacity it is created. Sorry, there is a typo, but it doesn't matter. Basically, it's a dummy hospital with the actual capacity X minus the limit capacity imposed, so that we have an extra hospital that's present in the compared to the original solution. And in this case, the algorithm is very simple. It's like an extension with the of the original solution. So that means the doctors now submit all their favorite contracts to the hospitals, even including the dummy hospitals. And the hospitals basically select their preferred contracts. So they select their top favorite hospitals, doctors, and then once the hospital has selected the contracts, the regions will confirm that the contracts are actually within the quote, within the regional quota. So if the contracts are within the quota, then this contract is called confirmed. And then once it's confirmed, then it's removed from all the contracts in the pool. So this process iterates until all the contracts are eliminated. So in this case, it solved the problem with this new algorithm or this new scheme of where there's a dummy hospital plus a like the original hospital with the limitation. So it's still a stable matching optimal to the proposing set. So this is similar to the original DA algorithm. And then, with the new setup, there is an extra capacity, basically time complexity. So because with the R, basically it's related to the number of regions because it's checking. And also because it's checking, it needs to loop over all the hospitals where we call M the number of hospitals, total hospitals, and N is basically the number of doctors. So you see, we'll iterate through all the new hospitals. And in that case, we are sacrifice a little bit like time to have we'll sacrifice a little bit of time for the extra redundancy that we can reduce.
Okay, thank you for Shengmu. And I'm Junjie. Let me introduce the application in school choice problems. Firstly, when you hear about school choice problems, you may think about college admissions. Yes, but we focus on student preferences this time. In other words, schools are treated as indivisible objects to be consumed by every student, and only student preferences constitute the welfare criteria. Okay, now we can try to get started by building the model. We have some schools X and some students I, and each school have a quota of available seats Q, and assignment means mu I equal to X means student I is assigned to school X. Okay, let us recall the meaning of unstable matching. Okay, student I is assigned to school X2, and student J is assigned to X1, and meanwhile, I prefer X1 than X2, while J has less priority for school X1 than I. So we may say it's an unstable matching. We should assign I to X1. But be careful, after fixing this unstable matching, I may get assigned to X1, but we can't send J to X2 directly because we don't know anything else about student J. So our goal is still to find a stable matching. It must meet three conditions. Firstly, it doesn't violate any priorities. It's a strong condition. We may need to execute deferred acceptance algorithm many times. And the second condition, every student weakly prefers his assigned seat to remaining assigned. It's an obvious condition. As for the three, no student we would rather be matched to a school has empty seats. We can assume a dummy student T and assign to the school X1, while the school X1 is what I prefer than my assigned. So T violates my priorities. So condition 3 is equal to condition 1. Okay, So let's think about what if we use traditional DA. Traditional DA, we may need two strict preference orders because we need to compare to matching under each type. So due to the preference of schools decided by laws and policies, we can see there are many indifferences classes. So for example, in Boston, there are mainly 4 indifferences classes for each school in the following orders. So they will use these classes to choose students. Okay, to simplify, recall our zooming. Schools are indivisible objects to be consumed. So we transform this indifference to students' preferences. Before we introduce the effect of this paper, let us know the formal algorithm RDA. It just try to break those interface classes in some extraneous ways so that they can apply basic DA. But because lots of these ways are just random methods, so it's called random DA, RDA. Okay, now we are trying to finish up our modeling. We add two profile. One is weak preference profile RI. Another one is strong preference profile PI. Strong preference profile means when XPIY, there's no YPIX. Okay, our goal can be transformed under this equation. Okay, mu I RI 0 means 0 means no school. I is assigned to no school. Okay, you may find out our model is not perfect because the result may be not so. And the result may be related to the selection order of different order P, right? This P. So we need to introduce this SOSM, student optimal stable matching. Firstly, it must be a stable matching. And secondly, mu is not dominated by any other stable matching mu hat. Mu hat dominates mu if mu hat I RI mu I for every I, and mu hat I pi mu I for some I. It means under some orders P, mu hat may be better than mu because mu hat assigned some better scores to I under this P. Okay. Up to now, we can try to update basic DA to our new algorithm and find the student optimal stable matching. We may say I desires X if I pi mu I. It means under order pi, I prefer X than the assigned state. And this is the definition of our stable improvement cycle. Okay, this is the transformation function. So now we can get our improvement algorithm. Step 0 is to find the most important fact P in our view and run the DA algorithm to get mu 0. And in the following step, we are given mu t sub 1, and let schools be the v vertices and draw the directed graph, where for each pair of schools x and 1 there is an h only if and only if there is a student I who is matched to x in mu t sub 1. And if there are any circles, it means we have found stable improvement circles. So we can try to carry out the stable improvement circle transition to obtain mu t. When there is no such circles, we can exit the algorithm. Okay. So how to evaluate our function? Let the students still be I, and the schools still be X. And this D means distance between the student I and school X. Alpha and beta are fixed common parameters. And this Z is normally distributed random variables with mean 0 and variance 1 for each I and X. Okay, and this 0 means dummy student we created with average tests. He may be indifferent to every school, and we compare every student with this student 0. Okay, so the paper provides a figure to show us the function is discrete and efficient. We can see when beta is 0, means we don't let the distance influence our u, and when alpha is around 0.5, we can get about 35% of improvement. So it's great. To compare with, we can choose the result of RDA. So the baseline is RDA's results. So we can see the improvement. Okay, these 5 papers are our references. Thank you for your listening.